welcome to lecture 29 of this course. So, today we are going to introduce the definition, the formal definition of a configuration. So, we have been using this term in several lectures, but we are going to look at the formal definition today. And using the definition of a configuration, we will define what we mean by a configuration graph. Okay. So, once again we will see that the concept of a configuration graph will allow us to explain many other properties of Turing machines in a much more efficient and easy to understand manner. Okay. So, first let us formally define a configuration. So, we know what a configuration of a Turing machine is. So, we have seen that. So, just to recall. So, a configuration is a tuple of the form state, tape contents and position of the tape head. Okay. So, this is essentially what is the definition of a configuration. So, a configuration graph once again as it is with the case of a configuration. So, a configuration, recall, that is only defined if we fix a Turing machine and an input to the Turing machine. Okay. So, let us say that we have a Turing machine M. Okay. So, defined for a Turing machine M with respect to an input, say x. Okay. So, this is what we mean, because for different inputs again the configurations can be different. Of course, for different machines the configurations will be different. Now, let us look at the definition of a configuration graph. So, a configuration graph of M so this graph is denoted as G mx is a graph whose vertices are the configurations of G with respect to x, and there is an edge from configuration C1 to C2 if the Turing machine M can go from C1 to C2 in one step. Okay. So, basically it is essentially a graphical way of modeling the computation of M on an input x. Okay. So, it is a graphical representation of the computation of M on X. Okay. So, basically if we have a transition from one configuration to another, in the graph there is an edge between the first configuration to the second configuration. Okay. So, it is a directed graph. Okay. So, now in this configuration graph, let us look at, so this is the definition of a configuration graph. Let us look at one more definition. So, a computation path is a path in GMX from the start configuration. Okay. So, recall once again from last lecture that there is a unique start configuration. So, the start configuration is the configuration where the state is Q0, the tape contents is the input that is given, that is X in this case, and the tape head points to the leftmost cell of the tape. Okay, so, it is a unique configuration. So, therefore, there is a unique vertex corresponding to the start configuration in GMX. So, any path in GMX that starts at the start configuration is known as a computation path. Okay. So, there can be computation path that goes from the start state to an accept configuration. Okay. So, that would be a accepting computation path. There can be a path which goes to a reject configuration, would be a rejecting computation path, and so on. So, therefore, the following proposition is very easy to see. M accepts X, okay, if and only if there exists a path or there exists a computation path in GMX from the start configuration to an accepting configuration. Okay. Because if there is a path from a start configuration to the accepting configuration, I can follow that path and that would accept the input X. If there is no such path, that is all paths lead to reject configuration, it means that X is not accepted. Okay. So, let us look at some properties of the configuration graph. So, properties and notations, if you make also. So, the first property, or I should not call it a property, it is more like an important observation, is that configuration graph is defined with respect to a Turing machine and an input. Okay. So, this is just emphasizing what I said earlier, that we cannot have a configuration graph of a Turing machine. Okay. So, that is something which is incorrect. So, if we have a Turing machine and if we fix an input of the Turing machine, only then does it make sense to talk of a configuration graph. Okay, so, it is a function of two quantities, the Turing machine and an input to it. Okay, so, given both these two, I can output the configuration graph. So, now let us talk about, let us try to understand how the structure of the computation graph looks like. So, if M is deterministic, then out degree of every vertex in GMX is at most 1. Okay, it cannot be more than 1, because essentially what this means is that if M is deterministic, is that from every configuration there is at most one configuration that you can go to. In the special case when the configuration is a accept or reject configuration, there are no edges going out, in which case the out degree is 0, otherwise it is 1. Okay. If M is non-deterministic, then out degree can be arbitrary. Okay. Next is what I just said, that so out degree of accept and reject configurations are 0, and this is actually an if and only if. If the out degree is 0, then it is accept and reject configuration, and the other side is what I mentioned. What else? What about the size of this graph? Okay. So, technically okay. So, let us try to understand this. So, what would be the size of the configuration graph of a Turing machine on an input? Okay. How large can it be? Okay. So, technically observe that it can be infinite, because it stores 3 quantities. It stores the state, of course, which is finite, but it stores the contents of the tape. Okay. Potentially you can on a certain input, okay, what you can do is that you can just keep on adding symbols to the tape, okay, without ever stopping. Okay. So, therefore, you just go into an infinite loop that keeps on increasing the tape at every step. So, the number of configurations can be infinite. Okay. So, technically GMX can be infinite, but if the size of the tape is bounded, then GMX is finite. Okay. So, suppose if we say that you can only access the first 100 cells of the tape, or you can only access, if you have an input n, you can only access the first n square cells of the input of the tape, then there are only finitely many possibilities for those n square many cells, and hence the size of GMX is also bounded. Okay, it becomes a finite graph. Okay. And the last point is that although once again by definition every configuration is part of GMX, but without loss of generality we can only look at configurations that are reachable from the start configuration. Okay. So, although I mean by definition the graph contains all possible configurations of the Turing machine on that input, but there are of course certain configurations which are not reachable from the start configuration. In other words, when you are performing the computation of the machine on the input x, you will never even reach that computation. So, what is the point of keeping them in the graph? So, without loss of generality, we can only focus on the configurations that are reachable from the start configuration. Okay. So, this we can always assume without loss of generality. Another point that we can assume without loss of generality is that the GMX has a unique start and accept configuration. Okay. Because suppose GMX, so technically of course GMX can have multiple start and accept configuration, but we can always add a new configuration. Okay, we can always, for example, in the Turing machine, I can add a new state for as the start state, which has the following property, that if the Turing machine entered the old start state, what I would do is that I would first clear the entire tape. Okay, I will erase the entire tape, move the cell to the leftmost cell of the tape, I move the tape head to the leftmost cell of the tape and then enter this new accept state. Okay. That would be a unique configuration because the tape contents are empty and the head is pointing to the leftmost cell. Similarly, if it enters a reject state, I can do the same thing. Okay. I can empty the contents, I can move the tape head to the leftmost cell and then I enter the new reject state. Okay. So, essentially I can have a unique, without loss of generality, I can assume that GMX has a unique start and accept configuration. Okay. So, so these are some properties that that are, I mean, that will be used when we talk of configuration graph of a Turing machine. Okay. So, let us look at, so we talked about deterministic and non-deterministic Turing machines, but let us just try to see an example of how their configuration graphs differ. So, here is what the configuration graph of a deterministic Turing machine will look like. So, I have the start configuration, so I will call it C start. Okay. So, let us call it C start, and by its nature the out degree at every vertex is at most 1. Okay. So, from C start I can go to a unique configuration and from here I go to another, and then from here maybe I go to a accept configuration, let us say C accept. Okay. So, therefore, it is 1. Of course, I can have a loop also, I can maybe come back to a previously visited configuration, that is also fine, but I cannot have more than one outgoing edge. Okay. So, this is let me write it here. Examples of configuration graphs. Okay. So, this is for a deterministic Turing machine. In the case of a non-deterministic Turing machine, I have C start. Okay. Then maybe from here I go to two different configurations, and then I come here, and then I go some configuration over here. Here, okay, maybe this is C accept, and this is C reject. Okay. So, there are many computation paths, one that goes from start to C accept, there is another going from C start to C reject, there is another going from C start to C reject, there is a third computation path that is also going from C start to C reject. Okay. So, this is the configuration graph of a non-deterministic Turing machine. So, in this case, do we accept the input x or not? What do we do? So, observe that in this case we should accept the input, because by definition there is a computation path that goes to an accept configuration. That is the definition of acceptance of a non-deterministic machine. If there is at least one computation path that goes to accept configuration, we accept it, okay. And we do not care, and if we would have rejected x only if all computation paths had gone to reject configuration. Okay. So, let us look at a quick application of this idea. So, we will state this as a theorem. So, the class of languages accepted by deterministic Turing machines and non-deterministic Turing machines are the same. Okay. So, of course, by definition non-deterministic Turing machines are more powerful than deterministic Turing machines, or I should not say more, but at least as powerful as deterministic Turing machine. But what this theorem says is that they are not any more powerful. Okay. So, they are equal in power. So, whatever we can do with a non-deterministic Turing machine, we can do with a deterministic Turing machine as well. So, how do we prove this? So, the proof idea is if I want to just state it in one line, it is to do BFS of GMX. Okay. So, suppose we are given a Turing machine, a non-deterministic Turing machine M, okay, and I am given an input x, and I want to decide whether x is accepted by M or not, which is non-deterministic. What I do is I compute the computation tree of GMX, okay, and I actually do not compute it all together, I just compute it as and when required. First I compute the start configuration, which is of course easy, because it is just the input, the start state, and the input head is at the leftmost cell. Now I look at the transition function of the non-deterministic Turing machine, and I keep on computing what are the children of the current state from each state. Okay. So, maintain a Q data structure to store the visited configurations of GM comma X. Okay. If an accept configuration is encountered, then halt and accept, and if the entire GMX is scanned without seeing an accept configuration, then halt and reject. Okay. So, that is the idea. So, basically what we do is we scan the computation graph level wise, first level, second level, then the vertices at the third level and so on. If we ever see a accept computation, we know that there is a path from the start configuration to the accept configuration, and we halt and accept. And if we exhaust the entire graph without ever visiting the start configuration, we then halt and reject, okay, because we know that there is no path from the start to the accept configuration. But what can also happen is that maybe it is an infinite graph, okay, maybe there is one computation path which never ends, okay, that can very well happen, in which case your deterministic simulation would also go on forever. Okay. It is a deterministic simulation which would also go on forever, which is still fine. Okay. But the point is that if there is a if there is an accept configuration, it will be at some level, and that level will always be encountered. Okay. So, I will stop here, and we will continue next time again.